Very good morning. We were here. So we were trying to establish the Cartesian product of n with itself is countable. So we have already shown n is countable. Okay. Now what we have here is let me go further and let me come back here. So if you recall, what is the Cartesian product is defined is x cross y is equals to the pair a comma b such that a belongs to x and b belongs to y. This is how the Cartesian product is defined. Now you know the set of natural numbers and you are having Cartesian product with itself. Okay, so and then you can enumerate them. So with you can go with 1. So you can 1 adjoin with all as possible natural number 1 comma 2, 1 comma 3, and so on. Similarly, for starting with 2 for okay, so 2 comma 1, 2 comma 2, 2 comma 3, and so on. Right? Then you have the you can say sequence of this 3 comma 1, comma 2, 3 comma 3, separated by commas, and so on. Okay, so now they are enumerated like this. Okay, so now what we are looking here, we are trying to use the counting principle. So how we are going to count? The count means we are trying to identify the position of m comma n in this scenario by following some method. Okay, so method is obtained is you are counting diagonally. So you know how to define the Cartesian product. Then n cross n is defined, means you know how to define now. Then what you are doing is you are enumerating the entries in this fashion now. 1 comma 1, 1 comma 2. So you are starting with first element you are fixing and then you are varying b. Then similarly second element, second entry like 2. So like you are making this column with 1, 2, 3, you are starting with first entry. And then you are making these all the possible pairs. Now, if you look at the first diagonal, number of elements are 1 here in the first diagonal and the sum of each entry is 2. Okay, correct. Now the second diagonal, if you look, and if you pick any of the member here, the sum is 3. Number of elements are 2. Means 3 minus 1. Similarly, 1 comma 3, 2 comma 2, 3 comma 1. That's the third diagonal. Okay, and that sum of each entry is 4. Means sum of the elements, right? A plus B, you can say. And how many number of elements are there? 3, and so on. So in the kth diagonal, so if I say this is the first diagonal, second diagonal, third diagonal, fourth diagonal, and so on. So if you look at the kth diagonal, the sum of the each entry is going to be k plus 1. So that is a kth diagonal. So this is the kth diagonal with sum. So because we are following this here is sum, and this side is a number of elements here. Okay, now what we are going to do is we are trying to identify the position of point m comma n in this scenario. Means you are counting and you are ending with somewhere, let's say here is some m comma n is there and you want to find the position. So means definitely you are going to count till its previous diagonal whose sum is m plus n minus 1. Okay, you count all the elements, then you will come into this diagonal and come to this here. Now, if you look at this pattern 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on. So, at which place in this diagonal, if you look at here, so this is this diagonal. If you talk about m comma n, its sum is m plus n, and the diagonal position is m plus n minus 1. Right? So this number that number of elements in this diagonal m plus n minus 1. Right? Now, but you are going to count till only this. this position. So what you do is you count all the number of entries in each diagonal till the sum is m plus n minus 1. So that m plus n minus 1, I'm just going to let's make the sum here is I'm going to enter with m plus n minus 1. The sum is m plus n minus 1, means the diagonal contains how many number of elements? M plus n minus 1 minus 1, that is m plus n minus 2. Then you will start counting from here. Okay, then you start from your first entry, second entry, third entry, and so on. This will be at which m place. So this is why. So what is h of m comma n is going to be, if you count all, if this psi function will give you the total number of elements till kth diagonal, means like that is going to be 1 plus 2 plus till plus k. So then this is equals to the position of this m comma n, psi of m plus n minus 2, because you are going to look at the diagonal, all the diagonal you have to go for m plus n minus 2, plus how many number of places you are moving now till m plus n. So that is how you will define the function h. Okay, so this is sum is, you know, this is k into k plus 1 by 2. Okay, and that is going to be again this is equals to m plus n minus 2 minus right, m plus psi of m plus n minus 2. Right. So m plus n minus 2 into m plus n minus 3 divided by 2 plus n.
So m plus n minus 1.
M plus n minus see,
Instead of minus 3.
Minus 3. Okay. This is minus 1. Yeah. M plus n minus 2 into m plus n. No, how it will be plus n?
Because sir, we are counting numbers now. So if you will put value 2,3 in place of m and n, then it would be the fifth term if we will keep n plus n.
No, see here. Suppose you are trying to get the 3,2. Okay. Now what you will do is you count this here, how many number of elements in diagonal, then how many number of diagonals are there, and how many number of diagonals are there. How many members are there, how many pairs are there in these 3 diagonals. Then what will be this? First is 1 comma 3, 1 comma 4, 2 comma 3, 3 comma 2. Okay, so what is varying, what you can do? So that is a first place, that is 1 comma 4. Second place is 2 comma 3.
2,3, yeah.
Third place is 3 comma 2. So which is varying is the first only, right?
First m.
Okay, so this is going to be plus n. So now this map will give you the definition of the function x from n cross n to n. Okay, and then we want to show that this function is going to be a bijection. Yeah.
If we instead of plus m, we can write plus n also, no, if we change the direction of the arrow.
Yeah, if you change the direction of the arrows, yeah, then you are counting on the thing. Yeah, that also possible. Yeah.
Okay.
Yeah. If you are counting in this way, it is going to be plus. If you are counting in this direction, upward direction, you can see here. In the previously, it was downward direction. We have how we have put it in the structure. Okay, so if you are counting from this side, yeah, definitely it is going to be n only. Okay.
Excuse me, sir.
Yeah.
Sir, I got what you taught, but the main doubt is why we are doing this. Means I'm not getting why we are doing like this proof for this question.
Like, okay, see, we have defined a function, so you have got everything. So the question, original question is, we wish to show that the set is n cross n is countably infinite. So how would we show that if this is going to be countably infinite? We have to find a bijection from n cos n onto n. That is need to show when you want to show that this is going to be countable. If you want to show a set S is countable, means you have to give at least a one bijection which is from S to N or N to S, whatever, on which way you have to go for. Okay, so this is why we are doing all this stuff. We are trying to identify a bijection, okay, for n cross n onto n. So
Sir,
that we can claim that that n cross n is countable. Yeah, tell me.
Sir, is it compulsory to show bijection from n cross n to n? Can't we show till z or any other means rational number or something like that?
Yeah, that is also possible. Why? Because that is also possible. If you have shown that the set Z is countable, then you have to show that Z is countable. Okay, because when you show that Z is countable, means that there is a bijection from, you can say, N to G. And if you take the composition here, so that what you are talking is G composed with F is from S to Z. That's also possible. That's also fine. Okay, because if you show that Z is countable, because then there is a bijection from Z to N, so it automatically gives you the same, it automatically proves the same thing only. Okay, so there is no restriction that you have to prove the bijection from S to N only. Then if you show that it's a bijection from N cross N to, let's say, Z, if you show, then you have to additionally show that is also counted. Okay, so there is an additional extra work now. But if you are able to find a very simple bijection from N cross N to G, then you are already given here what will be the bijection from Z to N or N to Z. How will you define that? You can use for constructing this bijection.
Sir, can I say that as we know n is denumerable, that's why we are using to prove n cross n to n. Is it correct?
See, if you say by words, see, sometimes it happens you say by words that, okay, this is countable because n is countable, and if you take a Cartesian product with the set of natural number, it has to be countable with this. See, the words is fine, but when you talk about the mathematics require proof. You can't talk about anything without a proof mathematical background. Okay, means suppose in future you are going to solve some engineering application. So there you are going to use some calculus, some epsilon, or some tolerance. You have to decide in applications to achieve your desired accuracy. Suppose you are going to create a bridge, and you want to see how much quantity of the cement should be mixed and how much quantity. So there is always a mathematics behind it. So when a mathematician meets you, he will definitely ask you, what is the guarantee that your bridge will not be broken? So you require a theory, at least in mathematical background, which actually give the gist of your work. That whatever you are doing, that is based on theory, and that is applicable, and that is it already have applied somewhere, and what you are getting. See, suppose you have the equation f of x equals to 0. Okay. Suppose you have the equation f of x equals to 0. If you want to claim that this equation certainly has the root, So what are the required condition need to be imposed on on this given function f, so that you can guarantee that there is always a root. So if you look at the graph, so it needs, see, whenever you're looking at the solution of f of x equals to 0, means the curve needs to cut the x-axis. So you say, sir, if the curve is like this, so it will definitely have the root, but it is not, means like you require just justification. Means you have some point, you have to some point here, and let's say some point is here. Like say this is point is A or B, and this point is, let's say, A. Okay, and where the function is negative. And now what is there is f of A is less than 0, f of B is greater than 0. What other condition you require? It requires the continuity in between. So you require f is continuous. If you have these two conditions, so there is a result that which is known as Bolzano's theorem. Okay, that shows that there is at least one root. Okay, that gives you guarantee that it has a solution. If I'm going in the interview, if he asks me something like why it is a bijection, okay, so what I will say, because every element has its unique position, uniquely placed. So when uniqueness is there, okay, so the other entry will not be placed at this position. That will prove the injection. Means that is going to be injective. Now, this entry will definitely have the unique position. So you will not get, means that will tell you the onto, means for every, so this is a counting 1, 2, 3, 4, 5, 6, and so on. You take any member P, some K, you will definitely find some entry there whose image is K. Okay, so onto is there, uniqueness will give you the feeling. So that is the way you can at most explain to your interview. Okay, or during your presentation. Okay, but if he asks you to detail, you have to work out. Yeah, am I clear to you?
Yes, sir.
Yeah, okay, fine. So we are now in position to show now that H is a bijection map. Okay, the very first thing we are going to show is H is injective. Okay, so let me show that this H is injective. So H, I'm just going to give the definition, M cross N to N is defined as H of M comma N time psi of M plus N minus 2 plus M. If you're looking from the downward, that definitely you can replace it by M as well. Okay, due to symmetry. Okay, right. Now we want to show that is an injective. So the very first thing we want to show that H is injective or 1, 1. So to show that H is injective, what you have to show that if, means you have to show that if you have two members M comma N and other member is M dash comma N dash, suppose they are not equal, then their H of M comma N also not equals to H of M dash comma N dash. And now you know how to compare these two. Okay, so what will happen then if M comma N is not equals to M dash comma N dash? Okay, then what will happen? Either, so but some could be equal, right? M plus N could be equals to M dash plus N dash, right? Or some is also not equal. So there are two cases now. Case 1, there are two cases. Case 1, so either M plus N is not equals to M dash plus N dash. Let's say first case. Or case 2, where our second case is, there may be chance that the sum is like 1 comma 2 and 2 comma 1. So they are not equal, right? M plus n may be equals to m dash plus n dash, but m is not equals to m dash. Okay, so there are these two cases. So we are going to do this, handle these two cases now. So if m plus n is not equals to m dash plus n dash, means certainly either this is less than or greater than. So without loss of generality, you can assume that this is less than. What is the meaning of without loss of generality? Means what? Means if you, instead of less than, if you do the greater than, doesn't matter. Means you will go with the proof in the same manner, just change the role of m dash and m and n dash and n. Okay, right. Okay, so let's assume that m plus n is less than m dash plus n dash. Now if you recall the property of psi function is nothing but the sum of natural numbers 1 plus 2 and so on k. So if you add one more point k plus 1, so what is the property of psi function? Psi function is increasing function. So we are going to utilize that property here. Okay, now also, so the note that m dash is greater than 0 and psi is increasing function. Psi is increasing function. So what will happen is now h of m comma n is equals to, by definition, that is equals to psi of m plus n minus 2 plus m, which is certainly less than equals to psi of m plus n minus 2 plus m plus n minus 1. N is a natural number, so n is greater than equals to 1. So n minus 1 is greater than equals to 0. Okay, so if you add something here, it's certainly definitely less than equals to this. Now, what is this? This is nothing but psi of m plus n minus 2 plus m plus n minus 1 is nothing but psi of m plus n minus 1. Right? Because we are adding one more point, one more number of diagonal elements in the next diagonal. So that is going to be totally psi is equal to psi of m plus n minus 1. But now, since m plus n is less than m dash plus n dash, okay, so that is, so and use the fact that psi is increasing function, so that's certainly less than equals to psi of m dash plus n dash minus 2. M plus n is strictly less than m dash plus n dash. So here is m plus n on the natural number and here is m dash plus n dash. So either m dash plus n dash is strictly less than. So if you add 1, so either it will reach to m dash plus n dash equals to, or it will be still less than, maybe some other natural number is there. Okay, the next natural number is m plus n plus 1. So whether this is sitting in this side or that side. So it cannot be go on the right of this m dash plus n dash. It can only reach to m dash plus n dash. Because this is a natural number, the sum is going to be a natural number. So like for example 1 comma 2. So if you add 1 plus 1, that is going to be 2 only. It cannot cross 2. If you add 1, 1 is strictly less than 2. Or if you take 1 comma 3 here, if you add 1, so there is a one more natural number 2. So 1 plus 1 is strictly less than 3 still. So you can't say if you add 1, you are sure that either is going to be equals to m dash plus n dash, or it is still going remaining on the left of m dash plus n. Okay, I think this is clear. So now this is going to be less than equals to psi of, so by using the property x1 less than x2 less than equals to x2, psi of m plus n minus 1 is less than equals to psi of m dash plus n dash minus 2, since psi is increasing function. Now, certainly this is strictly less than psi of m dash plus n dash minus 2, and use the property that m dash is greater than 0. And what is this is? This is nothing but h of m dash comma n dash. So it says that whenever m plus n is strictly less than m dash plus n dash, we are saying that positions are different. H of mn is strictly less than h of m dash comma n dash. So in this case, this proves the injectivity of the function h. Okay? Can we go with the second case now? If you have any doubt, you please ask.
Okay, sir.
Yes, sir.
Okay? Now you are confident about this. I hope. Okay? Right. Now, we want to discuss this second case. Now, case 2 is m plus n is equals to, so case 2 is m plus n is equals to m dash plus n dash, but m is not equals to m dash. Now, if you in the sum, if you are putting n, you are going to take with n is not equals to n dash. Okay, right. So how will you handle this now? Okay, so the m plus n is equals to m dash plus n dash means they are lying on in the same diagonal. That's what it means, right? And m is not equals to m dash means you are starting with 1, 2, 3, 4. M is sitting at different and m dash is sitting as for the place m dash is different. That's what the second case. And we want to show that h of mn is not equals to h of m dash comma n dash. So what you are going to now is, so I'm going to start with h of m comma n with minus m. What is the here that by definition that is going to be psi of m plus n minus 2. Plus m will get cancelled. And now since m plus n is equals to m dash plus n dash, so psi of m plus n minus 2 is also equals to psi of m dash plus n dash minus 2. And which is equals to h of m dash comma n dash minus m dash. Now since m is not equals to m dash, so m is not equals to m dash, so h of mn is also not equals to h m dash comma n dash. So this implies you know m is not equals to m dash. This implies what? H of n is not equals to h of m dash comma n dash. Okay, so second case was simple to understand. Now the second part, now we are going to show that h is surjective, means it's an onto map. Okay, h is surjective. Now for let's say for h of 1 comma 1 is what is adjoined with the 1, right? So for 1 you always able to find a unique 1 comma 1, so there is not a problem. Now what we have to see for p, let p is belongs to n and p is greater than equals to 2. Okay, means you take any natural number which is greater than equals to.
Sir, don't h 1 comma 1 comes as a 2.
No, it's the position of this. What is there is this is going to be, if you go by definition, psi of 1 plus 1 minus 2, right? And plus m.
Sorry,
M
sir,
is
I made a mistake.
okay. And psi x 0, if you want to define, that is you by convention you can define as 0, because there is no point, so there is no point. Okay, right. So let P belongs to n and P is greater than or equals to 2. So what we need to find? So we have to find, now we have to find an element in n cross n. So it certainly depends on P. So we are going to define with MP and NP belongs to n cross n, such that the image of this should be equals to P. Means it is sitting at the pth position, means if you're counting with the diagonally. Okay, right. So now we are going to prove this. Okay, right. Okay, now certainly the number is going to be, now clearly P is strictly less than psi of P. Psi of P is 1 plus 2 plus and so on till P. Okay, and now consider the set, consider the following set, which is certainly depends on P, which collects all the possible natural number such that P is less than equals to psi of K. So since this strictly less than psi of P, so there may be other natural numbers such that this is EP, means like P is less than equals to psi of K. There may be some. Now we observe what? EP is non-empty. Why? Because P belongs to EP. Okay, P belongs to EP. So EP is not empty. So there is one property attached with the set of natural number. So which we need to mention here, which is well ordering property for natural numbers, which says that every non-empty subset of n has a least element. Has a least element. So you take any non-empty subset of n, it has a least element. Okay, and this property we are using as an axiom, you can say, which we are going to means like assume that this is true. Okay, that you can be, see, largest element you can't say because it's non-ending. Maybe you will find a 2 comma 2 comma 2 comma 2 comma 3 comma 3 comma and so on. If you write and so on, you don't know where it ends. You can only talk about the list because every member of n is going to be greater than equals to 1. Okay, so it always has a least element that we are sure, and that is known as well ordering property. So since EP is empty, EP is non-empty, so certainly EP has a least element. Okay, so this implies EP has a least element, say KP. Okay, so it certainly depends on P, so that is why these suffixes are coming with P only, the notation. Okay, now since this is a least element and KP belongs to n, so if you subtract 1 from here, it is not going to be list. Okay, if it's not going to be the list, means it cannot, it will not go beyond P, it will always be low below. Okay, right. So using this fact now that it is KP is a least element for this set, what we can say since also not that p is greater than equals to 2. So then psi of kp minus 1 certainly strictly less than p, and that's going to be certainly less than psi of kp. P lies between this. Okay, and if you use the definition of psi, that is going to be psi of kp minus 1 plus kp. I can split this into this. Now we have to define carefully MP and NP. So how will we define is, so we define MP is equals to, so you see P minus psi kp minus 1 is strictly greater than 0. And since P and this are two natural numbers, okay, this is also natural number, this is also natural number. So subtraction will also going to be a natural number. So certainly greater than equals to 1. Okay, so we are going to define P minus psi of kp minus 1, which is strictly greater than equals, which will be greater than equals to 1. Strictly greater than 0. So it certainly is because difference of two natural numbers is again a natural number. Also, so what from here observe is 1 is less than equals to NP, and it is certainly less than equals to KP. Right? Why? Because from here, from the second relation, P minus psi KP minus 1 is going to be less than equals to KP. So you have the property of this NP. Now we define NP is equals to, now by using these two, so KP minus MP is strictly greater than equals to 0. Right? Is greater than equals to 0. So what you will define is KP minus MP plus 1. So that it is going to be a natural number. So difference of two natural numbers is natural number. Okay. So we are going to define that, you know, that is either equals to 0 or greater than 0. But to make sure that certainly greater than equals to 1, we are making this adding 1. Okay. Moreover, so this implies 1 less than equals to NP. And this also certainly less than equals to KP. Because KP is equal to KP plus 1 minus MP. So 1 minus MP is greater than equals to 1. So MP minus 1 is a greater than 0 number. So if you difference with the natural number, then certainly less than equals to KP. So that is also true now. Now if you try to see the image of this H of MP comma MP is going to be psi of MP plus NP minus 2 plus NP. So this is equals to psi of, now if you use the definition of NP here, what is NP is KP minus MP plus 1. So MP will get cancelled. 1 with minus 2. So what you will have is KP minus 1 plus MP. Now what is MP is P minus psi KP plus 1. So you psi KP minus 1. So this will be get cancelled with this here, and what is remaining is simplified form is. This shows that this is certainly going to define the bijection only. The next is we are going to learn the algebraic properties of R, which you also named as field axioms. Okay, somewhere you have may have learned that, or may have been told that R is a field. Okay, and so it requires some condition need to be satisfied. Okay, so these conditions are going to be mentioned here, which are you are going to use, like sum of two real number is real number, difference of two real numbers is real number, they are commutative, means a plus b is equals to b plus a. What are the properties attached with the plus sign? what are the properties attached with the multiplication. So these properties all are known as together will form an set that is known as field axioms. So these properties are very well you can get it from within a few minutes. So on the set R of real numbers, there are two operations denoted by plus and dot called addition and multiplication respectively. So that you are already aware that sum of two real number is real number. So it definitely goes to the set. Multiplication of two real number is multiplication of two real number is real number. So that also closed with respect to R. Okay. Now that is so. Now what is the first property you can learn is commutativity with respect to addition. So A plus B is equals to B plus A for all A, B in R. So whether you take A plus B or you take B plus A, both will be the same. Second property is associativity. So A plus B plus C is same as A plus B plus C. That is very easy to verify. Now the third property is existence of zero element. There exists an element 0 in R such that 0 plus A is equals to A equal to A plus. Means yes, the element is called to be a zero element when you are adding adding it to some member, you will get the same thing. Okay, means input is A, and if you are operating with the zero element, that is going to be the output is also the same as input only. So A plus 0 is going to be A only equal to A plus 0. So because this A plus 0 or 0 plus A because of commutativity. So similarly, you have the existence of additive inverse. Means for an element A, you are always able to find B in R such that A plus B is equals to 0. So this B is denoted by minus A. Okay, that is denoted by minus A. So that is how you will define the existence of additive inverse. So for each A in R, there exists minus A in R such that A plus minus A is equals to 0, equals to minus A. Okay, right. So these are the property associated with the addition. Okay, similarly, some of the properties are also attached with the multiplications. So they are as follows. So commutativity means A dot B is same as B dot A. Okay, right. Similarly, associativity A dot B, if you multiply first A and B and then you are multiplying with C, or you multiply B and C and then you are multiplying with A, they are the same thing. Similarly, existence of, so here you can't talk about zero element, here going to be unit element, right? Because you are going to give input, output will be the same. If you multiply by 0, you will get 0 only. So here you are talking about unit element. So you multiply by this a number, which means input will come as also, means it will result you the same thing only. So A dot 1 is same as A is equals to 1 dot. Similarly, you can go with the multiplicative inverse. So for a multiplicative inverse, you need to make sure that A must be non-zero. If for a 0, you don't have any inverse. 0 into 0 is 0. That's it. Okay. There exists 1 by A. So that at the starting you can say A dot B is equals to 1. Then you call that B is equals to 1 by A. Your notation is going to be B is equals to 1 by A. Or slowly you will also try to use the notation that A to the power minus 1. But you have to make sure that A must be non-zero. Now, these are the 4 properties attached with the multiplication. Now, one more property is there which is known as distributive law. Okay, means A dot B plus C is equals to A dot B plus A dot C. Okay, right, A dot plus A dot C And the left distributive, because you have distribute A from the left side, and the right distributive A plus dot C is equals to A dot C plus B dot C. So if you, this is the additional property which only real field has. Okay. Similarly, you can go with the extension of this, means you can talk about the XY plane. Then you can talk about the space. So when you will say a certain set forms a field, if it satisfies all of these 10 properties, so these are totally 8. So 2 more: left distributive laws, right distributive law. Okay, so that will, if you and you have to identify 2 operations, okay, so that it will be verified. Okay, right. So next we are going to give the examples, more examples we will look at, where you will say that there is a finite set which will be a field. Okay, so that we will explore in the next session. Okay, right. So we will do it in the next session. Okay, right. So if you have any question, you please ask.
Sir, can you give the any example of uncountable set?
Any example of uncountable set? Yeah, that's a set of irrational numbers.
Sir, can you repeat why bijection implies the set is denumerable?
Yeah, because see, because set of natural number is, what we have the definition. We have the definition that if you are able to find a bijection from a set S on to N, then we say that the set S is countable. You take set of rational number, okay, that are countable. Okay, so if you want to show that set of rational number is countable, you have to certainly show that there is a bijection for set of rational numbers onto N. You have 2 sets. You can relate them uniquely, means every member you can associate with the unique member from the your given set. It's not like you have associated 2 members from your set to a single member on the other side. It's 1 to 1, means they can be, means like you say, for example, you have your TA. So total number of students are 42. If you have the 40, right now I can see this here 42. So if you have a 42 number of TAs, so there is a 1-1-1-2 correspondence.
Sir, we can also do 1-1 mapping of irrational numbers to the natural numbers.
For rational numbers you can do. For set of irrational numbers you can't do. There is a result. Maybe 4-5 pages result is there. Proof. Okay, proof is there. There does not exist any bijection. And the Hardik is asking f from a to b bijective function, then a will be counted. If b is a set of natural numbers or b is a countable set.
So, sir, by proving f is a bijective function, we cannot say anything about b.
No, one of the set needs to be countable. Then only you can tell about the other set. Whether this is, if you are talking, see, we are talking about the specific thing, right? That is going to be countable. If we want to attach this property, other set needs to be countable. Then only you will be able to say. Because there is a 1-1-1-2 correspondence. You can attach one unique person to a unique person in the other set. That's how you, if you are able to understand this point. I think this is the right thing. Yeah, tell me if it is.
So, sir, if A is countable, we can say B is countable, and if B is countable, we can say A is countable.
Yes, yes.